Okay, let's get started today. We've got a lot of material to cover that's really important for homework assignment 1, so we've really got to get to it. I'll do this really quick. Okay. Questions about project 2, homework assignment number 1? Questions? Yeah.
Would you rather typed out or handwritten?
What?
Typed out or handwritten?
I would prefer typed out for homework 1, and I think the TAs and I would also agree. You gotta think what makes it easier for us to give you points, right? So if it's handwritten and it's hard to read your handwriting, that does not put the people grading your homework in a good mood. So yeah, it'll just be easier for everyone. Unless you need to draw like a parse tree, that's probably the exception that you can hand do. More questions, homework projects? Yeah.
First question, 6th question. So you said that you have to show the working. So it's a very long working. It's about 2 pages.
For homework?
Yeah, I've written it down. Like returning you got to return the token as well. So that long string.
Yes, yeah.
So do I have to submit those 2 pages?
If you want credit, right? I mean.
Okay. No, it's handwritten, so it's not.
That's fine. You can put your answer there and say like your notes are attached. You don't have to retype your notes, but it's up to you. If you think we can read it, right? Then
Yeah, I'll just post the notes.
okay. Then yeah, that's what because if your answer is wrong, we're gonna have to go look at your derivation and everything that you did, right? So if you can't read that, then you might want to type it up. Other questions? Cool. All right. So we're going to start where we left off on Monday. So we've been talking about can we use a regular expression to define grammars and the programming constructs that we're really interested in here. And hopefully this example at the bottom here kind of shows you that, yeah, maybe regular expressions aren't the right tool for the job because it looks like a proper regular expression that we just defined up here, right? To define what a program is, it's statements. One statement that we're interested in is an expression. An expression we're defining as numbers or IDs or decimals followed by an operator, followed by either a number or an ID or a decimal. But that fails on this case of the string 1 plus 2 plus 3. And so it turns out, we're not going to get into the exact specifics, but it turns out that regular expressions aren't actually sufficient or expressive enough to capture all of the programming constructs that we want to be able to define when talking about and analyzing a language. So we're not going to go into the details, but you can, if you look, you can find proofs of this, that regular expressions are just simply not expressive enough. They can't express or describe the language that we want to be able to match. And so if you think about it, kind of the example I like to give here, and once again I'll reiterate, we're talking about the regular expressions as we define them in this class, right? So we're not thinking about any of the extensions to regular expressions that might exist in current programming languages. So kind of the motivating example is how do you write a regular expression to match balanced parentheses, right? So if we think about it from the end working back, what we want to define is we want to define some regular expression R that the language that's described by R is let's say the empty string, 2 parentheses, 1 left paren, 1 right paren, 2 left parens, 2 right parens, 3 left parens, 3 right parens. So can somebody write this regular expression? Yeah.
No, because it would require predicting the future.
It would require predicting the future. The future
It
input?
would require you to know this, like, beyond the next token. Because you don't know.
Beyond the next token. Yeah, that's one of the reasons I would say. Right. So, anybody think you can? Yeah.
Can you use the union operator and write the union of I is equal to 0 to n of left parenthesis dot union of I is equal to.
So the only thing we can use, right, is the concatenation operator, the dot operator, the OR operator, the bar, or the star operator. Those are the only three operators we can use to construct a regular expression for this. So, right, so the bar means 0, or the star means 0 or more, right? But that's not a finite number, right? It just means 0 or more repetitions. So maybe you can kind of think about it. This is why we're not going to get into the details, but there's the regular expressions we've defined have no concept or no idea of counting. They can't say one left paren followed by one right paren, or two left parens followed by two right parens, right? You can define those individual regular expressions, but you can't write a finite regular expression that captures that idea of we want balance. So the same number of left parens followed by the same number of right parens. So kind of it's really about this idea of counting. We can't, which kind of goes to the look ahead, right? We can't, when we see the left paren, we can't look ahead and see, oh, there's 3 or 4 left parens, and that means I want 3 or 4 left right parens to close those out. Does everybody kind of see that? Questions? So still, regular expressions are very powerful, right? But the things that we want to describe, like matched balanced parentheses, can't be described by regular expressions. So that leads us to our next topic, which is context-free grammars. And these are grammars that are going to allow us to express these programming language constructs that we're really interested in. And so we're going to define these. We're not going to go super formal like we did on regular expressions, but I want to give you an idea of what's involved here. So the syntax for context-free grammars, so they're going to be defined by a series of rows, and each row is going to be called a production. And we're going to have what we're going to call non-terminals on the left side of the production, followed by a right arrow, followed by non-terminals and terminals on the right. So in all of our examples, non-terminals are going to start with an uppercase letter, and terminals are going to be lowercase, and we're going to think of our terminals as tokens, right? So tokens are defined by regular expressions, and so we already know how to take a raw input string and using our lexer, given a set of tokens, be able to pull the tokens out of there in sequence. So now what we're going to define this grammar on is essentially the tokens. And so S will typically be the starting non-terminal. So okay, this is kind of high level, very abstract. So let's look at an example. This maybe hopefully makes it a little bit clear. So the example for matching parentheses. So we have one production rule that says S produces the epsilon, the empty string. Okay, so that'd be one production rule. So in this case, what's the non-terminal here? S. Yeah, it's on the left. You know it's a non-terminal because it's on the left, and you also know because I've said that all the non-terminals will be uppercase. Okay, we have another rule that says S produces left parentheses, S right parentheses. So this is it. This is our grammar, our context-free grammar for defining that language, for defining the language of equal amounts of left parentheses followed by equal amounts of right parentheses. And this kind of makes sense. So the way I kind of try to think about this is I look at the grammar and I say, okay, well, whenever I see an S, I can either replace it with the empty string, nothing, or if I see S, I can replace it with a left parentheses, an S, and a right parentheses, right? And I can continue doing that, but so left parentheses, S, right parentheses, that's not a string, right? And this is where we get the term non-terminal, right? It's literally in the name. So you can't stop and generate a string with a non-terminal in it. The non-terminals are part of the context-free grammar, but not part of the strings that are defined by this grammar. So what can we do? Well, we can replace that S with an empty string, an epsilon. And so I'll show an example in a second. But I just want to clarify. So we're going to actually reuse the bar operation one more time. So we're going to be able to write these context-free grammars a little bit more succinctly by combining the same production rules with a bar. So this means S can produce either left parentheses, S, right parentheses, or it can produce the empty string. Does that make sense? Questions? Okay, we can go back. We'll go back here. So let's walk through an example to see if we kind of can understand intuitively what this grammar means and what kind of strings it describes. So when we have this grammar, here in this case, the same grammar, right? S produces either left parentheses, S right parentheses, or S produces epsilon, the empty string. So we're going to define derivations of the CFG. So these are going to describe how we use the CFG to generate a valid string that is defined by this grammar. And this is going to be pretty simple. We're going to start on the very left with the start non-terminal. So in this case, it would be S, yes. So only one non-terminal here, so you have like I guess 100% shot at guessing. Well, maybe 50 if you also tried epsilon, but that's not a non-terminal. So we're going to start on the left with S, and we're going to show the series of steps where we apply one of these rules to S and how we end up with a string at the end. So, and we're going to separate these, so for notation purposes, the single arrow here is going to be describe the grammar, and a thick double arrow is going to describe a step in our derivation. So for instance, we can go S derives epsilon. So why can we do that? Yeah.
Because one of the options is S produces epsilon.
Exactly. So one of the options in the context-free grammar is S produces epsilon. So if we start with S, we can derive epsilon just by applying that rule of the context-free grammar. So, I just see I made a mistake here. Okay, so this is wrong. Why is this wrong? Let's go. Somebody raise your hand? Yeah.
Terminal cannot derive. That's the right side of production.
Right. So these at every step, at every double these double thick right arrows, it has to be a rule from our rules, right? So do we have the rule of S produces left parentheses, epsilon right parentheses?
No.
No. Right, so that's wrong. Let's say I did it on purpose. So I'll go in and fix it in a second, and you can tell me how to fix it. So this isn't right, but this is a string that we will generate. So let's go to the next one. So we first, okay, this one is more right. So here we have 3 steps. So we're going to start with S. We're going to apply the first rule. S produces left parentheses, S right parentheses. So we're going to apply that rule once. Then we still have an S left, right? So we still have a non-terminal, so we can't stop. So now we replace that S with which rule? 1 or 2. You can put your fingers in there. So 1 would be this one, 2 would be this. 1. Can you guys actually see this? Okay. Make sure I wasn't gesturing myself. So yeah, 1. So we're going to replace this S with the same rule, left parentheses, S, right parentheses. And then we're going to replace S with what? Which rule in this case?
Epsilon.
Epsilon, the second one. Right. And so doing this, we can generate strings that are represented by this context-free grammar. Right? We could keep doing this. We could keep choosing rule 1, and every time we then choose the rule 2, now we have a string, and so we say, okay, that string's in our context, the language described by our context-free grammar. Questions? So, do you agree that this actually describes that language that we wanted to, of matching parentheses, numbers in parentheses?
No.
No. Why no?
Because it only covers the instance of a single matched case, as in you have one statement that just has an increasingly large useless parentheses.
Okay,
You're
correct.
not actually using the parentheses to do anything.
That's a good point. So I guess I should be more specific. So does this describe, let's go back. Sorry, I hate it when I have to do this. Does this describe this language?
Yeah. Okay. Yes.
Yes, so it describes a language that we could not define using regular expressions, right? So it defines the language of equal numbers of left parentheses followed by equal number of right parentheses. But yeah, it does not match what we kind of want is any expression with balanced left and right parentheses. Those will be more advanced and those will come later. Okay. So derivations. Okay, so let's look at another example questions before we go on to the next example. Okay, let's look at this example. So now I'm going to cheat a little bit, and we're not going to start with S. We're going to start with expressions. So here we're defining expressions. So we're going to define an expression as an expression can produce either an expression followed by a plus sign followed by an expression, or an expression can produce an expression followed by a multiplication sign or the star followed by an expression, and an expression can produce a number. So here, right, the star is not the regular expression operator, right? Because now we're kind of past the regular expression point where we're dealing with tokens. So you can think of the star as a token or representing the actual textual star. And the same with the plus. So does that make sense? So this actually, so what does this describe? What does this expression describe? You want to say that? Yeah. Anyway.
You can set up multiplication and addition.
Yeah, so the question is, does this match our earlier example with regular expressions of 1 plus 2 plus 3?
Yes.
Yes, does it? Gotcha, you tell me. So I guess the other way to phrase that would be, does the language described by this context-free grammar contain that string 1 plus 2 plus 3?
Yes.
Yes.
Yeah. Okay, so let's look at some derivations. So how can we, so we're going to look at, we're actually going to do a slightly different, I think it's 1 plus 2 times 3 is what we're going to use. And so if we derive it, so we start with an expression, right? We're going to apply one of these 3 rules. So if we apply the second rule, what's going to be after this double right arrow?
Expression, star expression.
Expression, star expression, right. And then let's say we want to then, we're going to, so now we have 2 non-terminals in this rule, or this derivation, right? We have the first expression and then the second expression. So we can, once again, I cheated. Okay. So once again, if we wanted to, let's say, replace that last expression by 3, the string 3, which of these 3 rules would we choose?
3.
The third one, number, right? So we may say that, okay, expression multiply, expression, the star operator, and 3. So is this first, are we done? Is this a string in our language?
Still have non-terminals.
Right, we still have a non-terminal here, exactly. So let's say we replace that by rule number 1, then what's the string going to look like? Expression plus expression times 3. Right, so at each step we're applying one of these rules. And then let's say we replace the second expression here with 2, the string 2. So now we're going to replace it there. And then we're going to, let's say we replace the first expression by 1. So we're going to have, so are we done here? Yes? No? Anybody say no? We have more to do? So yeah, now here we have a string that's in the language described by our context-free grammar. We have the string 1 plus 2 times 3. Pretty cool, right? So questions on context-free grammars, how they work, how we can derive strings, yeah? Do we need the parentheses here? I don't know, what does everyone think?
Technically we don't.
Technically we don't? Why?
There is already mathematical precedent set.
Who's talking about math? So right now we don't need parentheses, right? Because all we're doing is generating a string described by this grammar, right? So at this point it doesn't mean anything. You know, it all depends on how we describe the grammar and then later how we want to interpret that grammar. So yeah, so I guess phrased another way, if we intended this to represent expressions of mathematical operators, do we need parentheses? Hold on to that thought. We're going to leave it for a little bit because we'll talk about it in a second. So the question kind of is, well, then what are we doing with these? What are these derivations for, right? So that would be one thing. So it's important. So the way I think about it is these derivations describe kind of how are, in some sense, proof that this string is in this language, is in this grammar. So if I say, show me that the string 1 plus 2 times 3 is described by this grammar, well, how can you do that? Well, you start at the start and you keep deriving, applying rules until you end up with that string. And so that's a proof that, hey, this string actually is in this language described by this context-free grammar. And you can also maybe, you can kind of look at this and convince yourself that by applying these rules and even though these are infinite, right, by applying all these rules, you could generate all strings described by this grammar. Because you could keep, maybe always choose rule 1 until you choose rule 2, and then you can kind of generate all those strings. Whether you ever stop would be another matter. Okay, there's two important concepts to get across here because they're important when talking about, talking about doing the derivations. So how did I decide which expression to expand and apply one of the production rules to?
Seems like you went with the right one.
Seems like I went with the right one most. Is that true? Did I? Good pattern matching. I did not. It was not intended, but it's kind of I just did it arbitrarily, right? I mean, there's no. I at least didn't give you any rhyme or reason. I'm gonna have to change this example again. Great. Cool. So yeah. So at this point, so it's just you're choosing a non-terminal, applying a rule. But we're going to define two different types of derivations which actually do follow that thing where we're either going to call it a leftmost derivation or a rightmost derivation. And these concepts are pretty easy. They're very much self-explanatory. So in a leftmost derivation, we're going to always expand the leftmost non-terminal. Right? So if we have, once again, our context-free grammar, so the question is, that could be asked on a homework assignment or an exam would be like, is this a leftmost derivation of this context-free grammar? No, why? Somebody want to raise a hand? Yeah. 1, 2, 3. This one? This one. Let's go, let's count here. 1, 2, 3. So this step or this step? Okay, this one. So in this step here?
Yes.
Oh, that's what happens when you really want to click on something to highlight it. So in going, okay, so applying the first rule, right, we're applying the second rule, we're applying expression goes to expression times expression, right? And then here, we're expanding the rightmost, in this case, expression to 3. So yeah, so in this case, saying, so this is not a leftmost derivation because of this second derivation when we chose to expand not the leftmost non-terminal. Does that make sense? So you just always expand the leftmost. And it'll be hopefully clear why this distinction matters. Okay, is this a leftmost derivation? Is it a valid derivation first? Yes? This is good. I should like have papers that I write and like put sentences up there so that you can all like spell check and grammar check it. It's very good at finding mistakes. I like it. Okay, so is it a valid derivation? Yes. We're always applying one of the rules in the grammar there. I hope it is. It's meant to be at least. Is it a leftmost derivation? Yes. Is it? Anybody say no? Anybody want to argue that it's not a leftmost derivation? Yeah.
It's about the expansion of non-terminals, but we are doing for the terminals as well.
So it's about non-terminals when we're expanding terminals. We expand, well, so yes, okay, so maybe,
From step 3 to step 4.
what was that?
From the step 3 to step 4, we are expanding the terminals as expression 1 as 1.
Oh, so you're talking here?
Yes.
Yeah. So this is, so in this case, we're expanding expression to a non-terminal, and a non-terminal in this case would be number. So I'm kind of making the simplification step that we don't need to go from number to 1, right? So number is a token. You can replace number with 1, and we know that 1 is a token, and because num is the token that we defined previously, right? So we know that the string 1 is in the token num. So that's, I'm making a little shortcut step. But yeah, you could replace all the numbers here with just num, the token num, and it would be the same. But yeah, we don't expand that 1 again to something else, right? Because so the whole point of context-free grammars is there's never a terminal on the left-hand side. It's only non-terminals on the left-hand side. So anytime you see a non-terminal, you know exactly what you can replace it with. You can replace it with something on the right-hand side. But you never replace a terminal, which is implied in the name by terminal, right? So you finished, you terminated derivation. Whereas non-terminals, you haven't. You have to keep going. Does that make sense? Questions on this? Okay, who wants to guess what the next slide's title is going to be? Rightmost derivation. Awesome. Got a series of mind readers here. Good, yes. So the opposite of a leftmost derivation would be a rightmost derivation. And so the definition is once again very similar. So you always expand the rightmost non-terminal. So once again, with our context-free grammar here, I may ask you things like, is this a valid derivation? Somebody said no. Somebody want to say no? Which step is invalid? It could be invalid. Just text on the screen. Is it a rightmost derivation?
Yes.
No? No? Who wants to go no? Yeah.
Because so first step you do exp times exponent times exponent, then next step
Expression.
times 3.
Mhm.
The next step you expand the leftmost expression, so it's neither. So it's
But
So-
he's already expanded the rightmost non-terminal.
So somebody want to raise their hand and
that's not rightmost though.
reply? Yes.
That expression is the only expression left. It's only non-terminal, so that is the rightmost expression.
I wasn't even thinking.
So yeah, so it's actually the same scenario in the beginning, right? So all we have is an expression. That one non-terminal is both the leftmost non-terminal and the rightmost non-terminal, right? Because it's the only one. That's a good, it's definitely something that if it wasn't that way, that'd be like a sneaky thing to mix in there. So does everybody understand the question and the answer? Cool. Okay, questions on derivations, leftmost derivations, rightmost derivations? Yeah.
Are there derivations that are apart from left hand? Like if suppose somewhere down the middle you break up the order, does it become neither leftmost nor right?
Yes. So, for instance, if I expanded this middle, like if I expanded rightmost for 2 and then I decided to expand the leftmost by expanding this expression non-terminal here, then yes, that would be it would be a valid derivation, but it's not either leftmost or rightmost. So yeah, something can be, so one thing is it a valid derivation or not, right? Did we actually apply all those rules properly from the context-free grammar? And then, is it a leftmost derivation or is it a rightmost derivation? Okay. So where we're kind of heading and where we're trying to go, right, is we want to be able to take these sequence of tokens and turn them into what I've been calling a parse tree, so that that can be interpreted by the rest of our program interpreter, I'm going to call it very broadly. So we can also represent derivations using a parse tree. And as I said, hopefully it sounds very familiar because that's the goal of what we're talking about here, is how do we take a sequence of tokens and turn it into a parse tree. Okay, so what is a parse tree? So we have some derivations, so I'm going to assume at this point we're pretty familiar with the context-free grammar rules that we've talked about with expressions. Yeah, so if you have questions, I don't know, maybe I can put it up there or something. But there's 3 rules, it's not too terrible. So what we have this derivation, and so we're going to represent this derivation on a tree data structure. And the root of our tree is going to be the starting non-terminal of our derivation, or of our grammar, right? So the root is going to be, in this case, an expression, which is a non-terminal. And all the children of this, so for any node in our parse tree, all the children of that parse tree are an application of one of the rules in our context-free grammar. So which rule did we apply first in this derivation? Yeah? You have to speak up. Expression, the first derivation here? Yeah, so expression is produces expression star expression, right? So looking at the derivation we have up here, that's represented by the very first step here, where we applied, I want to say it's rule 2 in that context-free grammar. So how many children is our expression root of our parse tree going to have? 2? 1? 2? 3? You want to say 4? 2? Anyone? Okay, so someone want to say 3? Yeah.
That would be the expression, the second would be the operation, and the third would be the expression.
Yeah, so that's good. So we're going to have 3, and all of the children, a node is either a terminal or a non-terminal. So here we're going to have 3 nodes that are the children of the root node, and that's going to be expression star expression. So judging off of the derivation, so we've essentially, you can think of it as we've applied that first rule, that first step in our derivation above. So applying the third rule, which of these expressions are we going to look at first as having a child? Yeah. The rightmost. So the rightmost. And how many children is it going to have?
1.
1. And what's the value going to be? 3. Perfect. Okay, so what's the difference between the colors?
Terminal versus non-terminal.
Yeah, terminals and non-terminals. So I'll try to do that. It may not always happen. And you don't have to necessarily make that distinction on whenever you're creating a parse tree, but I thought it would help explain. So yeah, so the non-terminals here are blue, and the non-terminals are blue. The terminals are green with like a white border, in case you're colorblind. So another question would be, does any of the non-terminals, like the star, are they going to have a child? Somebody said no. Why? Do you want to explain?
So it terminates.
Yeah, the terminal terminates. It doesn't ever generate anything, right? So the parent-child relationship here means that the children were generated by applying one of the rules in the context-free grammar. So there's no way to expand the star, right? We don't have any rules because it's a terminal. That's part of what we said the definition was. Okay, what's the next thing we're going to expand here? The left expression, right? The remaining non-terminal. At this point, we don't really have a choice. But we can also see in the parse tree, right? We can look at this next step and say, okay, we had expression times 3. Now we're going to expand that expression, and how many children does this expression have? This node? 3? What are they going to be?
Expression plus sign expression.
Expression plus sign expression. Great. So yeah, here we have that. So are we done?
No.
Why?
Still non-terminals.
Right, we still have non-terminals. Our tree isn't complete, right? The tree doesn't describe the derivation, and so we have to continue. So which of these 2 expressions are we going to expand first?
Rightmost.
The rightmost, what's the value of that?
2.
2. Great. And then the final one?
1.
1 on the, I guess, leftmost expression here. Cool. So you can tell you're done, right, parsing, because all of the leaves of the tree, right? So what's a leaf in a tree? Not like philosophical or like, I don't know, like don't describe a leaf in a real tree. And like mathematically, in the way we think about in computer science trees, what does it mean for a leaf to be in a tree? Yeah? Has no, yeah, no other nodes connected, so no children, right? Yeah, so a leaf node is a node in the tree that has no children. And we know we're done when all of the leaf nodes are non-terminals, right? So that means, huh? Terminals, yes. Okay, they are, yes, they are terminals and are not non-terminals. You want to avoid those double negatives. And so maybe you can see that we can actually generate the string represented by this parse tree by doing a depth first search and going through this tree and going through all the non-terminals. Here you can see visually left to right. You can also do, if you think about a depth first traversal, and we can get the string represented by this parse tree. So what does this represent? So this parse tree is what we're trying to go for as far as what the goal here of our parser is. So what does it represent? I mean, I know I kind of say, well, it doesn't mean anything until we give it meaning, but what would be the natural kind of, assuming we're defining this mathematical language, if I gave you this parse tree, would you be able to compute this expression? Does somebody want to like briefly describe how they may go about that? Yeah. And do what?
So like if he's like on the bottom left,
Mm-hmm.
right plus 2 and the
Right. So yeah. So what would be the result? Let's see, math right off the bat, huh?
what be the result?
Yeah. 9. Yeah. So yeah. So you would. So the intuitive way of how to interpret this, right, is, you know, obviously we have to give it meaning, but we'd say, okay, well, this expression in this, let's say, subtree in the lower left, well, I know how to calculate 1 plus 2, right? So I have an expression, the operator is plus, and the values that I'm adding together are 1 plus 2. And so this expression, the result of that would be 3. Right? And so if I said, okay, what's the result of 1 plus 2, and the operator on this expression would be multiplication, right? Multiplied by 3. Well, I can do that. 3 times 3 is 9. Yeah?
So it doesn't understand.
Oh, sorry, I was going back here. Let's go. All right, you go first, and then.
Okay, sorry. So it doesn't understand precedence yet, right?
At this point, all we're looking at is a parse tree. It's trying to think of how might we interpret. Like if I gave you this parse tree, could you calculate it and, you know, do the calculation that it describes? But so I guess the question kind of maybe underneath the surface there is, does this parse tree also, like, is this parse tree ambiguous in the sense that, would you ever return anything else other than 9 if I gave you this parse tree and told you to calculate it? What was that?
By changing the derivation, like from rightmost to leftmost, would we change it like you're still using depth first search to change that order of operations?
So the question is, if we change the derivation, will we change the order of operations? The answer is going to come up in a second. Yes, absolutely. But giving this parse tree, right, this parse tree is unambiguous. So by changing the derivation, you're going to actually generate a new parse tree. So if I gave you this parse tree, it's unequivocally that I mean I want you to add 1 plus 2 first, and then multiply that result by 3. Does everybody see this? Because they're farther down in the parse tree, that is, if you think about it, a mathematical expression of 1 plus 3. I know how to do that. And I know how to take the result of that and multiply that by 3 with this expression. Questions about the parse tree in general, kind of what it means, how we can create one from the derivations? Yeah?
Why do we use the rightmost derivation here? Is that just because you said we were going to, or is there any reason why you use it?
We may see in a second. It's a good question. As far as right now, no. Other questions? Okay, good. I think we're doing good on time. We're going to hit everything we want to. Okay, so I guess have we talked really about parsing at all so far? No, not really. What I've showed is I've tried to show how we can define a grammar, right? So the grammar defines some language, some set of strings. And we've seen how we can use derivations to derive a string that follows that grammar. And we've seen how we can take those derivations and then create a parse tree out of that, so we can see maybe an alternative representation of a derivation. But right now we've only been looking at how we can actually generate these strings, right? Applying these rules, these production rules in the context-free grammar to generate strings. But what are we really trying to do? Yeah?
Recognize the strings that are in the grammar?
Yeah, so we want to, our input, we're not given a context-free grammar trying to generate strings. Actually, what we really want is we have a series of tokens coming in. You can think of it as a string or a series of tokens, and we want to say, does this match our grammar? And so we need a way to turn a series of tokens into a parse tree, which then we can pass the parse tree off to the next part of our program interpretation, and it can then interpret that or execute it or transform it, do any kind of cool stuff. So parsing is really the process of determining which derivation or parse tree is meant from a sequence of tokens. Now, it's probably pretty clear because we've touched on it a little bit so far, but there's two major parsing problems here, right? And that is, one is ambiguity in the grammar. So right now we want to take a string. So think about it, way at the start of this process, we want to throw in a sequence of bytes, just a string. And then, but at the end, we want to have we want a parse tree, a single parse tree. And so we're going to talk about ambiguity in a second. The second biggest problem is efficient parsing, right? We want to be able to do this quickly and efficiently because, well, I mean, practicality reasons, right? So it would be very annoying if it took your compiler like 5 to 10 minutes to compile a small, simple program. So we want to be able to actually do this process efficiently. Okay. So we're going to touch on ambiguous grammars for a little bit, and then we're going to shift gears, so it'll be clear. Okay. So going with our grammar that we've been talking about so far, this context-free grammar, the question comes up, how do we parse the string 1 plus 2 times 3? Assuming that we already have tokenizers to split it up into the tokens num and the token star and the token plus. Yeah?
We can do it in two ways, either use rule 1 or rule 2.
Right, so yeah, starting from the top, right, we can either apply rule 1 or rule 2. So I'm going to show this in derivations. So this one would be applying rule 2 first. So applying the multiplication rule. And the second one would be the similar one, applying the addition rule first. So it's kind of, derivations are nice because they're very succinct, but to me they're hard to visualize, like what is this, how would I turn this into computation? Whereas like a parse tree to me is much more intuitive to understanding, oh, this means these things happen together and these get passed up there. So we're going to look at the parse trees of these. So if we have 1 plus 2 times 3, well, we first have the other derivation we've looked at, right? Where we first have the multiplication and then plus is added, right? So this was the parse tree that we were looking at. Can you in the back read the text there, more or less? Okay, cool, thanks. Okay, so for the other tree, what's the other parse tree that we can write here? So how many, oh, yeah, so it's going to be expression, what expression? Plus, yeah, plus. And then this leftmost expression is going to go to 1. And the rightmost expression we're going to now expand to expression, star expression. And The middle expression is going to go to 2, and the last expression is going to go to 3. Awesome. Okay. So we can see that mathematically, right, if we wanted to calculate or execute this parse tree, we get 2 completely different results from this string, right? So we get 9 in the case on the left, and on the right we get 7? 2 times 3, right, which is 6, plus 1, which is 7, right? So here we're grouping the 2 and the multiply first together, and then adding that result there. So this is kind of what we're trying to get here. This is intuitively what we mean when we say it's ambiguous. So there is, if I give you a single string, there are 2 valid parse trees from that string. So is this a good thing? No. Yeah. Okay, so we're going to define it more or less formally, and this is why we talked about leftmost derivations and rightmost derivations. So a grammar is ambiguous if one of 3 conditions hold, and they're actually all the same. But there either exist 2 leftmost derivations, or so different, obviously. So 2 different leftmost derivations, 2 different rightmost derivations, or 2 different parse trees for any string in the grammar. Do I have a dangling parentheses there? Yes, I do. Okay. 6. Okay, good. So does this make sense? Yeah. Exactly. Yeah. So I like to think of it as parse trees. Because to me, it's just a lot easier to think about that way. Yes, because the parse tree describes really what order things happen in, and what things happen together, and what things, you can think about expressions again, right? These expressions will ultimately define the computation. So if you can create 2 different parse trees from the same string, then your grammar is ambiguous. And so the tricky thing about derivations here is just that it has to be 2 leftmost derivations or 2 rightmost derivations. So if you say the grammar is ambiguous because you can do a leftmost derivation and a rightmost derivation, that doesn't mean it's ambiguous, right? Because we've seen the case where if you have a single non-terminal, it's both the leftmost and the rightmost derivation, right? So intuitively, that kind of makes sense. And B. So then the other question is, what about just any random derivation, not left or rightmost? And it's because of, we're not going to get into details, so I won't expect you to know, but a leftmost derivation corresponds to a unique parse tree, and a rightmost derivation corresponds to a unique parse tree. If you just do the derivations not leftmost or rightmost, then you don't get that property. So if you think about like these grammars, right, the order, once you're left with expression star expression, it doesn't matter which one you derive from a non-terminal as plus or 3, right? So you have 2 different derivations that describe the same parse tree. Does that make sense? Okay. Kind of hopefully fun little exercise we can have for like 5 minutes. Is English ambiguous?
Yes.
Anybody want to say it's not? You could maybe have that. If you do think it's not ambiguous, you probably haven't met people who English is their second language. Yeah? It's going to depend on the author. So yeah, I guess your answer is, well, if you were very, very, very careful, you could write maybe a subset of English that is very unambiguous. Yeah, so let's look at this sentence. I saw a man on a hill with a telescope. So how many different meanings? Is there just one meaning of this sentence? So what does the sentence mean? Somebody give me a meaning. Let's play some fun English games. Yeah.
You could say that you saw a man on the hill by looking like through a telescope.
Right, so one way would be, I saw a man on a hill using my telescope. So I have a telescope, I'm looking through the telescope, I saw a guy on a hill. Yeah?
It could mean that you just saw somebody in half who had a telescope in their hand on top of the hill.
Yeah. It could be you're sawing a person in half on a hill. You're on top of a hill. You're sawing a man in half with a telescope. Probably easier if you broke the telescope first, but yeah, so that's another one. What about, yeah?
You saw a man on a hill that had a telescope on it.
Who has a telescope on
The
it?
hill.
The hill, yeah. So one would be, you are not looking through a telescope, but you see a man on a hill, and there's a telescope on the hill next to the man, let's say, right? Is that what you're saying? Yeah.
Or an observatory or whatever.
Yeah, or he's,
The hill possesses
I
a
didn't-
telescope.
right, the telescope is on the hill. Yeah.
You saw a man while standing on a hill with a telescope.
Yeah, so you saw the man while you're on the hill with the telescope, right? So you saw a man on a hill with a telescope, yeah. Yeah. Is there any more? I saw some hands over there. Let's go middle, yeah. Yeah, the man has a telescope, right? Maybe you saw a man on a hill with a telescope and the telescope is pointing at you. So like he's using the telescope. Maybe the telescope is on top of the man. Maybe he has it on his head, right? You see a man on a hill with the telescope. Does that work? I think so. Yeah. Exactly. So yeah, when using the saw as the verb, right, now we can do the same thing where it's like, well, we're either sawing him with the telescope, or you're just sawing the man on a hill, and the man is holding a telescope, right? Yeah. I think that would count. Any other ones? Yeah. Is your accomplice? Oh yeah, like the telescope. Yeah, that'd be, you're like anthropomorphizing the telescope. So maybe it's even creepier. It's like you're crazy and like the telescope's telling you what to do. All right, so you see how crazy and dark and weird we can get by dealing with ambiguity in a language. That was a lot of fun. Anybody have other things? Anything else? I think we've kind of exhausted all the permutations. If you think of one, let me know. That's be really interesting. Okay, so I think it should be pretty clear from this example, right, that ambiguity is not desirable in a programming language. In English, I'm not a philosopher or an English major, but I'd argue that it's kind of nice having the ambiguity because you can derive humor from that. You can derive, a lot of interesting, you can create slang words that mean half of one thing or that sound like, anyways, all kinds of cool stuff. But in a programming language, it would be a nightmare, right? So like that would mean that you write one string and your compiler gets to decide how it wants to interpret that and do that execution. If you told your compiler to go, well, I guess it doesn't work with C, but if you told the compiler that you saw somebody on a hill with a telescope, and it may go report the police to you, it may ask you if you want to take a picture of the guy on the hill, if the telescope was nice, I don't know. So with the programming language, right, when we're trying to program instructions to our computer, this would be terrible. Does anyone want to take the opposite opinion? That would be good. I mean, I don't know about you, but I have enough problems programming as is. I don't need the compiler not understanding what I mean when I tell it. So yeah, we don't want the compiler to try to have to infer what you meant or to have two different ideas for whatever string. Like when you say print 10, you want it to print out 10 every single time and not decide to change to print something else, or maybe you meant to print it in Morse code on a paper and not on the console, right? So that would be very annoying. Okay, so at a very high level, there's two broad categories of parsers. There's where we can work what we call bottom-up parsing, where we start from the terminals in our language and we build up to the start. So you can think of it as like growing the tree from the bottom up and seeing how can we construct a parse tree just from looking at the terminals. The other way, the alternative there would be top-down parsing, where we start from the starting non-terminal. You can think of from the parse tree, we start at the root of the parse tree, and we think, can we grow a tree structure down, applying all those rules to match that string? And so in this class, we're going to focus exclusively on top-down parsing. So the only parsing we're going to look at or think about is top-down parsing. Okay, so what is it? Let's look at an example. So I've got it. Okay, we're going to be totally fine on time. Okay, so we're going to look at a context-free grammar. So here we have the production rule. S produces A or B or C. So what are A, B, and C here? Non-terminals, right? Capital letters. Okay, we have the rule A can go to little a. What's little a here? Terminal. Perfect. Okay, we have the rule B can go to big B, little b, or C. And then we can have the rule C can go to big C, little c, or epsilon. So, questions about the grammar? So, is it ambiguous?
No.
I don't know. Yeah.
I did not understand how B can go to B cos that point because the right side won't be the
So this is very similar to the S goes to left parentheses, S right parentheses, right? So it's just about replacement. So all we have to do is whenever we see a big B, we can replace it by either a little b or a big B and a little b. Obviously, we won't be able to do that forever. We have to terminate at some point to get a string. Yeah?
It depends if your operations are commutative.
It depends on what operations.
Whether you have ambiguity in your language.
No. No, ambiguity is not a property like commutative, associative, right? Those are concepts we think about afterwards. I mean, those are just at the language level, right? I mean, just at the context-free grammar level, we don't have any of those concepts. So we're going to see later about how we can like go back and fix those ambiguity from our grammar by essentially enforcing those rules in our grammar, like designing our grammar in such a way that those rules are naturally come out of it. But I guess I should have mentioned, we're going to set ambiguity for aside for a little bit because I have to get to some stuff so that we can talk about homework because it's covered on the homework. So that's what we're doing right now. Yeah.
So big B, little b is a non-terminal with a terminal, or is it a new non-terminal together?
Good question. It is a non-terminal, the non-terminal B followed by the non-terminal B followed by the terminal lowercase b. And another way, so since I've said that this is the grammar, right? So there's no production rules on the left side for like big B, little b. So that would be another way to clue. But yeah, that's a good question. Yeah.
Because big A can only go to the terminal little a, how come we can't? Why do we have to find that rule to the same as S goes to little a or big B?
Yeah, so the question is kind of about optimization, right? So we have a rule, big A goes to little a. Well, why don't we just replace any big A's, get rid of big A altogether and just use the non-terminal little a? Yeah, you could definitely do that, but it's just for examples. Like, yeah, there's no limitations on what kind of context-free grammar you can describe as long as you have a single non-terminal on the left and production rules are terminals and non-terminals. Those are the only restrictions. So you can do this, you can make a very long context-free grammar that boils down to this. Any questions? So what are some strings that this language can generate? A, B, B, C, epsilon. Yeah, that's good. Cool. Okay, so we're going to think about this as a top-down parser. And so right now I want to give you an overview of where we're trying to go with top-down parsing. And we're going to get more into the details later. So I'm going to define it as a function called parse S. So you can think parse S. So this is kind of like pseudocode, more like pseudo Python code. So you can think there's a function called parse S that we're going to call first to parse our grammar. So what does our parser use? Tokens, yes. Where do we get tokens from? What? The lexer. Yeah, exactly. So we get tokens from the lexer. So we're going to call the method on our lexer getToken. So here we're going to get the next token in our grammar. And then we're going to check, hey, if the type of this token is lowercase a, then I know what to do, because the problem is right now, when we're trying to parse S, we have three choices. Do we apply rule S goes to A? Do we apply rule S goes to B? Do we apply rule S goes to C? So what we're going to do is we're going to peek at this first token, and we're going to say if that token is a little a, well, then we're going to put the token back, and then we're going to call parse A, and parse A is going to have its own parsing mechanism. It's going to be very similar to this. And then we're going to check end of file. So why do we check the end of file?
See if that's the only one we have.
Yeah, because that would be an error. So here we're going to say the next token better be an end of file, otherwise we have a syntax error. Because in our grammar defines, if you have an A, it's only a single A, and that there should be an end of file at the end of that. Does everybody see this? Kind of get the idea here? Okay. So then, if we have a B, ooh, let's see. I may have made a mistake. Okay, so we're going to unget the token if there's a B. We're going to parse B. Well, I think we're fine. And then we're going to check the end of file again to see if we've matched the end of file. So we can assume that parse B knows how to go and parse all of the rules of its grammar. Okay, yeah, we're fine. Okay, so then the same thing. We're going to check if that token is a little c. Well, then we're going to put it back, and then we're going to call parse C, so parse C can handle how it parses its production rules. And then we're going to check the end of file. So what if we get an end of file? Is it a syntax error? You want to say it louder? Yeah, no, it's epsilon, right? So is epsilon a valid string in this language? Yeah, why? Yeah, S goes to C, C goes to epsilon, right? So epsilon is in our language. So then we do some end of file stuff, whatever. What if we get any other terminal or token here? Is what? Somebody? Parse error, yeah. Yeah, so if we got anything else, it's a syntax error, right? Because we know just intuitively looking at this language, that string better start with the token A, B, C, or end of file. Otherwise, it's not a valid program. Does that make sense? Kind of intuitively? Okay. So now we need to go real quick so I can give an example. Okay. So, okay, it's kind of a big word. I mean, not big, but there's multiple words here, right? Predictive recursive descent parsers. So recursive descent is just what we saw, where we start at the top, and we're going to recurse for every rule. We're going to say call parse A or parse S. You can have parse A call itself. We'll get into examples there. Predictive is important because it's efficient, and it means that we only have to look one token ahead to know which production rule to apply. So there's no backtracking, there's no guessing about which rule to apply. And so to determine so now the question is, well, so how do we know if our context-free grammar has a predictive recursive descent parser? Or can we define, like, is any possible context-free grammar recursive descent parsers? The answer is no. So we need help with the following two functions. We're going to define first here alpha, where alpha is a sequence of grammar symbols. So a sequence of either non-terminals, terminals, or epsilon. And what first is going to return, it's going to represent what is the set of terminals or tokens that can begin strings that are derived from alpha. So we'll see an example in a second. We're also going to discuss on Wednesday the follow set. So a follow function is defined for a non-terminal, which says what tokens, what non-terminals, the set of terminals, and here we're going to represent end of file with the $, that can appear after this non-terminal. Yeah. I can't hear you.
Do you mean next Wednesday?
Yes. Right? Today's Wednesday. Yeah, Wednesday. Next Wednesday. We're not going to talk, we won't get to it today. Okay. Yes. first sets are on the homework. That's why we got to cover them now. Okay, so here's the intuitive example that I'm going to give first, so we can think about what these mean, and then we're going to step through excruciating. We're going to describe the rules and then go through an example. Okay, so here's our context-free grammar from earlier. So we wanted to find first sets on all of our non-terminals here. So we wanted to find first of S. So, okay. So what, if we just look at S, can we decide what non-terminals can start a string that's derived by S? Yes, can we? Just looking at this rule. Not really, right? Because S can derive A, B, or C. So we really need to know what they derive. Whatever they derive first, then S can also derive that first. So we're going to leave it for now. And for A, it should be pretty clear. What's the first A, right? So all strings that A can derive, looking just at A, start with lowercase a. What about B? Yeah. Small b. What about A? Can B, the non-terminal B, by applying rules, can you ever derive a string that starts with anything but a B?
No.
No. So the first set of B is lowercase b. What about C?
C and epsilon.
C and epsilon by the same reasoning. So we look here and we see that C can only ever derive strings that start with a lowercase c or epsilon. So now, putting these all together, can we define what the first set of S is? So it's going to be the union of all of them, right? So it's going to be A, B, C, and epsilon. So a little bit of preview. We use these first sets to construct that parser I just gave. Because we can use this and say, hey, I know if I see an A, then it's got to be, I apply production rule A. Okay, so how do we actually calculate this? So we're going to do this in an iterative fashion. And we're first going to start out by setting the first set for all non-terminals in the grammar to an empty set. Okay, so that's where we start at. And then we're going to apply the following 5 rules to each of the non-terminals. And we're going to continue doing that until the first sets do not change. So until we've applied all the rules to all the non-terminals and we get the same first sets. I'm going to show an example. But here's the rules. So what's the first set of a terminal? Terminal, yeah. So the first set of x, lowercase x, where x is a terminal, is the set containing x, right? It makes sense. So if you tell me what's the first terminal that can start a terminal, well, it's the terminal. Okay. The second rule is the first set of epsilon is the set containing epsilon, by similar reasoning. The third rule, if we have a production rule of A produces big B, so big B is a non-terminal here, and alpha here is a sequence of terminals or non-terminals. So if this is a production rule in our grammar, then we add the first set of B minus epsilon, so taking out epsilon if it's in the first set of B, and unioning, when I say add here, I really mean union it with the first set of A. So why does this rule make sense? Or does it? Yeah.
Because if the big B results in an epsilon, the first is the little a.
Right, so there's 2 things here. So why do we add B to A? Right? Well, the first thing is anytime I see an A, I can replace it by B. So whatever B starts with, A has to start with that same thing, right? Because B is the first non-terminal in that string, in that production rule. And I take out epsilon because there could be this alpha afterwards where there's other stuff there. So we'll get to what we do here in this case, but this is just, these are very, yeah.
What if you have like BC?
We'll see in a second. Okay, so this is a very complicated-ish mathematical statement saying that if we have a production rule of A goes to a series of non-terminals from 0 to I, and epsilon is in everything in the first sets of 0 through I, all of those B's, right? So if A can produce these series of non-terminals and they all start with epsilon, well, that means that wherever the next one is that doesn't start with an epsilon, we can actually add that first set to A's first set. So basically, I think of it as, this rule 3 says that we can add B0 minus epsilon to A, right? Right? I mean, this is just a special case of the previous case. So we can add B0 to A right away. So the first of B0 minus epsilon, we can add that to A, the first set of A. But if B0 can produce an epsilon, that means that the first non-terminal could be from B1. And so we can add B1's first set minus epsilon to the first set of A. And then if B1, so this is an iterative recursive process, right? So if B1 has epsilon in its non-terminal, that means that the next non-terminal, B2 in this case, we can add its first set minus epsilon to A, and we can continue going out as far as we need to. Okay, then the last rule has to deal with, yeah?
So even if any of those B's that produce a non-terminal is not epsilon, just that epsilon
Is in it. They can produce a non-terminal, which means that they might, and so we have to deal with that case and go to the next non-terminal. Yeah. So then the question is, well, what happens if all of them are epsilon, right? So if A produces a bunch of non-terminals and they all can produce epsilon, then we can add epsilon to A's first set. Does that make sense? So that means, yeah. Yeah. We don't care at this point. So we can apply each of these rules in isolation. So yeah, we'll apply. So if bi plus 1 happens to have epsilon in it, well, we apply rule 4, and then we apply rule 4 again with I plus 2. And then if I plus 2 has epsilon in it, we apply it again with I plus 3. Okay, so let's walk through an example. I'm going to show the rules as we use them. So we have a slightly more complicated grammar here, right? We have S goes to A, B, C, all uppercase. A goes to C or D, CD, or lowercase a, big A. B goes to little b. C goes to little c, big C, or epsilon. D goes to little d, big D, or epsilon. So to calculate the first sets, there we go. We first are going to set all of the first sets to the empty set. And so to calculate the first set of S, we're going to apply this first rule, this rule 3. So we have the production, S goes to BA. So here, S is A, and A is B here, right? So we're going to add, applying this rule, we're going to add the first set of A to the first set of S. So what's the first set of A? So we're only doing this iteratively, right? So all we have right here is this initial, right? So what's the first set of A that we've seen so far?
Empty set.
The empty set, right? So we add the empty set, we get the empty set. Cool. Okay, none of our other rules apply, so A doesn't contain epsilon, so none of those rules apply. A is also not epsilon, A is not a terminal, so we're done. So going through the first time, the first set of S is the empty set. Applying this to A, so we look at the production rules for A and we see, okay, A goes to CD. Well, C, so we add the first set of C to the first set of A. But we also have another rule. We also have A goes to lowercase a, big A. So then we add, using rule number 3, we add the first set of little a, which is little a, to the first set of big A. And so that's applying rule 1. So we get A. And we're going to do the same thing with B. So that same thing happens, right? We're going to get lowercase b. We're going to do this with the first set of c. So what are we adding to the first set of c? C and epsilon, exactly. What about d? D and epsilon, great. Okay, the first set of s, so we apply rule 3 again. So we apply the first set, we add the first set of a to the first set of s, which is a, right? We're going to get a. And then for the first set of a, so we first carry over a, right? So we always have a. So we're going to add the first set of c to the first set of a, right? So what's the first set of c? But we don't add epsilon, right? Because we haven't gone all the way through. It's only if we get all epsilons all the way through. So first we add c, but then because c contains epsilon, then we say, well, we also have to then add the first set of d. So what's the first set of d? D epsilon, but remember by this rule number 3, we're going to remove epsilon. So here we've added a, c, and d. And now we apply rule 4 to add d, and then we apply rule 5 to then add epsilon. Why? Because c and d all contain epsilon. That means the first set of a contains epsilon as well. Great, so b doesn't change, should be fairly clear. C doesn't change, so we have C epsilon. D also doesn't change. Now, because we've changed the first set of A and the first set of S, we have to do this again. So we go through it again and we apply, okay, what's the first set of A? So what are we going to add to S? CD, we're not going to add epsilon because the rule says we're going to remove epsilon here. So we're going to add, from A, we're going to add A, C, and D, exactly. And then we apply this rule that says, well, A can contain an epsilon, so when we move to the next non-terminal, we move to B. And so we say, we look and we add B's first set minus epsilon to S, which is B. So do we go on and look at C? Right, B does not have epsilon, so we stop there. We don't go on anymore. And we get A, C, D, and B. And then we apply this same reasoning to A. The first set doesn't change. We apply it to B. The first set doesn't change. We apply it to C. It doesn't change. We apply it to D. It doesn't change. So do we go one more time? Yes, there's one more column. It should be very clear. But why do we go one more time? Because we changed the first set of S. So we go through and we do the same thing. We add the first set of A. Okay, that's already in there. We add the first set of B. That's already in there, but B does not contain an epsilon, so we don't go to C. And so we get that set. We go to the first set of A, first set of B, first set of C, and we finally hit a fixed point. We didn't change anything, so we're done. And these are the first sets. Thank you. Sorry for going late. I apologize.